Hey, so this is Mack 1. I'm doing the lab report on the motion of a falling object. So in this lab, we're dealing with the velocity update formula and proportionally the position update formula, though not as important in this one. Um, so what we're looking at here is we're dropping an object that drag will have an effect on. And we're using two different computational models to look at this motion, one that takes into effect drag and one that doesn't. Um, One thing to note here is that drag is not constant. As the velocity increases, so too does the drag force, and as we'll see later, until the point that it equals the gravitational force. Here's the first model, the one that doesn't take into effect drag. You'll notice that I am not taking into effect mass in my force equations, and that's because we're dividing it here and multiplying it here. You can just take it out, it doesn't make a difference. And the mass, yeah, it just doesn't really make a difference. Specifically because, as we see over here, neither does the drag formula take that into effect. I find this constant here with a little bit of trial and error until it looks right. I make the f-net equations are just here added together, sort of abstracting out the unit vector and doing it with just subtraction and addition. But you can see here that as the velocity is updated up here, so too is the drag force, so it increases the more times we go through the loop. You'll as well see here that the time stops here. That's because that's when the hat hit the floor. As well, the increments are in a odd part so that it matches the frames of the video. That's more relevant for the next slide where I show the graphs. This is just me dropping the hat. You'll see there's a piece, it is hard to see, but there's a piece of tape around where my mouse is hovering up here, marking it at 2.1 meters to make everything nice and neat. Here we have the graphs. Yellow is the computational model with drag, red is the one without, and blue is the experimental data. Notice that all three are different, and that's because even when taking into effect drag, the hat doesn't behave the way the model wants it to. A hat is irregularly shaped, it has holes in it, there's wind currents in my room, and my clicks are inaccurate. You know, the video is blurry, I have a bad phone. That's just some of the small errors. As well, it was, for some reason, very difficult for me to drop the hat without giving a small amount of horizontal velocity. Whether or not that's because the hat is sort of acting like a wing, I'm not sure. But that too could have a small effect on the variability here. Of note that the one without drag is the lowest, and that makes sense because that means there's no opposing force, so obviously it would fall the farthest and fastest. What does it mean? This first graph is the one that takes into account drag, and we can see that it has a slightly concave shape. This makes sense because the force is non-constant, and so the velocity, the acceleration isn't constant. In fact, it is decreasing here, and of course on here the slope is constant. So when would terminal velocity happen? We see that this is a concave shape. It'll approach some asymptote, and when the velocity is constant, that is the definition of terminal velocity. We see this here when we make the time go longer than it should in the computational model, unlike in the experimental data. And we can see that it bottoms out here at close to 12. Here we have a starting velocity, and here we don't. It doesn't matter because that's just not a part of the equation. But we do see that, you know, obviously when starting closer to 10, we get a closer look at the data, but it doesn't really matter. We can see the same things either way.